So, we're on page, or not page, we're on the 5.8 section of our notes. All right, we're going to run through this, not super quick, but pretty quick, just because we do have a 2-hour early dismissal today. Don't have a full amount of time. It's going to be tight. We'll get through it here. Okay. So, the derivatives of the 6 inverse trig functions fall into 3 pairs. All right. Right. So we've got like essentially the two, well, arcsine, arccosine, right? Arctangent, arccotangent, and arcsecant, arccosecant. Okay. In each pair, right, the derivative of one function is just the opposite of the other. Okay. When listing the antiderivatives that correspond to each of the inverse trigonometric functions, you need to use only one member from each pair. Okay. So in other words, to integrate these, because we can kind of pull any negatives out, we don't need to worry about arccosine, arccotangent, or arccosecant here, because if it was a negative thing that we're integrating, we just pull the negative coefficient out front, make it positive, so that way we can just end up with arcsine, arctan, or arcsecant there. Okay, that kind of deal. All right. There are your rules, though. Okay, there they are. All right, so we recognize this, right? This, is in the form of arcsine. Okay, arcsine, it's the square root in the denominator. The number squared comes first, then your functions minus your function squared. Okay, compare that to the arcsecant, which is the function squared under the square root minus the number squared. Okay, and then of course the function in front of the square root as well. And then finally for arctangent, right, that's just when you add your number squared plus your function squared there. Okay, remember from like way back when we did, arcsine, arctangent, arcsecant. All right. Notice in front here, right, some, differences among the 3. Only 2 out of the 3 have a 1 over a. I don't really have a good way to help you kind of like remember that, these are the ones that have 1 over a. Okay, the arcsine does not have a 1 over a out front, though. Only the arctan and arcsecant do, okay? They all have the u over the a, okay, except for arcsecant has the absolute value of u over a. It's a little bit, you can kind of, help remember that the arcsecant has the absolute value of u. Just like when you take the derivative of arcsecant, you end up with the absolute value of u in front and the square root of u squared minus a squared. So, as far as like memorizing this, these, you just will need to have these down, right? Okay, it's helpful if you remember those derivative rules, the integral rules, or follow pretty much from that, right? It's the reverse of those. So, anyway, let's see these in practice. Okay, so we'll focus here on letter A, okay? And so looking at these, so these first couple here, we're going to focus just on like, these are inverse trig already, okay? And so therefore, we're just going to like match these up, right? Later in this section, we're going to be looking at like, these could be anything. And so how are we going to integrate, any of these things? But for right now, we know these are inverse trig, so let's just make them match, right? So for example here, letter A, all right, what does it look like the format of this integral is going to match up with? The arcsine, right? We have our number minus our function squared here. Now, what I recommend for everyone, because a common mistake here is to get like what a is kind of mixed up with what the number is that you're given here. So this 4, is this a? No. Remember, this 4 is a squared. So I would recommend you rewrite this as dx over the square root of 2 squared minus, and then even the x, I know it seems kind of silly to do that, but I think it's helpful just for your purposes to see, maybe even a good idea to say, okay, a is 2. Just to have that in your mind, okay, like for your, if you know your formula, if you have your integrals down or whatever, your antiderivatives down, writing out a is 2 can be helpful, again, just organizing your thoughts. Likewise, I'm going to say, u, let's say just let u equal, we'll say x here in this case, right? Because that's the thing that's being squared. Okay. Yes, Gabe?
Does it always have to be squared?
Yes. If you look at your formulas here, the a needs to be in a square function, and then u also needs to be squared. So you need to figure out what your u is as if you're going to square it to make it match, what you've got right here. That makes sense. So yes, good question. Okay. So just like that. For these inverse trig, of course, that's got to be true. All right, so du here is just a nice and easy dx, so there's nothing we need to worry about as far as our u substitution is. So I can just rewrite this if I wanted to, again, as du over the square root of 2 squared minus u squared, like that. Okay. And so we integrate this, And we go right, and that matches exactly to our formula right here, right? A is 2, u is x, and so when we go to integrate, it's going to be arcsine of x over 2 plus c. Or u over 2. I guess I should start with the u over 2 because I had that first, and then I'll resubstitute in. Oops, sorry, off the screen. Okay. Okay, and that's all there is to it. There is the integral. Okay. So far, so good? Okay. So letter B then, what does it look like?
Arctangent.
Right, so I mean, for sure we can throw out, it cannot be arcsine, it cannot be arcsecant. What is like the big thing that's missing here for it to be any of those two things? Square root, and maybe we could also even say subtraction, right? There's no subtraction here, right? Both arcsecant and arcsine require some square roots and some subtraction there, so we can throw those out, and it looks like, we do have a sum of just two things, okay? Now, you notice here, right? Again, in the wild, if I were to throw this problem at you without the context of we're talking about inverse trig, you might look at this and say, oh, Mr. Wig, we should let u be 2 plus 9x squared here. Just let the whole denominator be our u. But if I take the derivative of this, what do we end up with? The du would be 18x. The 18 is no big deal, but do we have an x dx here that we can, utilize? And the answer is no, right? So it would be, we don't have an 18, we don't have an x dx, we just have a dx there. And so we can't use that u substitution. This is inverse trig, the arctangent. Okay? So right. So what is a going to be in this case? Good. The square root of 2. Okay? And then our u is going to be what?
3x.
3x. Again, good. The quantity that's going to be squared to give us 9x squared is 3x. And so du equals 3 dx. We don't have 3 dx, we just have dx. I'm going to move the 3 over, make it 1/3 du equals dx. So now it lines up with our substitution we're going to make. And so we get 1/3 integral du over, and then I'm going to make this the square root of 2 squared plus u squared, like that. Okay, again, just for our purposes here, we're just learning this stuff. It's helpful to write it out like that. Okay. This is arctangent, right? It matches up. There's our a squared right there. There's our u squared, and so it's 1/a arctan u over a. So 1/3 from the integral times 1 over the square root of 2 for the 1/a part. Arctangent of u over the square root of 2 plus c. Okay, which we can simplify some here. So 1/3 square root of 2 arctan of 3x over the square root of 2 plus c. Okay, don't forget we're doing indefinite integrals, right? All those need to be at plus c. Okay. All right. And then letter C. All right, moving on from there. Letter C. What trig function does it look? Inverse trig function does it look like we're going to use here? Arcsecant. Okay, so again, in the wild, on your own, without the context, you might think, oh, the x squared minus 9, that's inside a square root. So Mr. Wid said in the past we're supposed to pick our u to be like inside of another function. X squared minus 9, that's inside another function. Okay, let's see here. Du is going to be 2x dx. Do I have the 2? I can just move over, so it's 1/2 du equals x dx. I have an x dx. I can use a u substitution here. But why is this x dx not going to match up to this right here? It's 1/x. That x is in the denominator, right? Okay, the x in the denominator is 1/x dx. This is just an x dx. This, in order for this to be to substitute for this, we need the x up here. The x is in the denominator. We can't just move it up there, right? It's 1/x, completely different. So, right? This is the arcsecant. What gives it away? Square root of kind of two quantities being subtracted, the function minus the number, and then also the function in front there as well. Okay, so what is our a in this case? 3. Okay, and we're going to let u equal, what will our u be in this case? Just x, right? So du equals dx. No fancy, footwork we need to do there. It's just a nice, easy substitution. So 1 over u, square root of u squared minus 3 squared du. Okay, and so this goes right into, and I'm gonna run out of space. I'm gonna put it down here. The 1 over 3, our a value, arcsecant, absolute value of u over 3 plus c. In other words, 1/3 arcsecant, absolute value of x over 3 plus c. Oops, that's not a negative, so it'll be equal to. Okay. Questions on any of that? Easy peasy, right? Relatively. And Mr. Witt's helping us out. Unfortunately, integration is not usually straightforward. The inverse trigonometric function formulas can be disguised in many ways. Remember that rewriting to a formula is a key to integrating, okay? To integration is the key, okay? So you want to rewrite to match a particular formula, okay? So, again, when you do a problem like this, the temptation, when you first come across it, you might think, I don't know, let's maybe let u equal 1 minus e to the 2x. Okay, not a bad idea, right? We have 1 minus e to the 2x. It's inside the square root. We know the derivative of e to the 2x is another e, and we have another e up here. But let's see what happens. When we get that du here, what is the derivative of 1 minus e to the 2x? Well, what's the derivative of 1? 0. What's the derivative of e to the something? So e to that something again times the derivative, so times 2 dx. Okay, no big deal there. We can take care of coefficients. But do we want to use a u substitution of 1 minus e to the 2x here? No. We do not have e to the 2x. We have e just to the x. And there's no amount of manipulating that we can do here to make those kind of match the way we need them to, right? Okay, the 2 here, no big deal. We can pull the 2 out front. We can, divide the negative 2 over and get e to the 2x, but dx, but we have just e to the x. So this is not the substitution we want to do. Okay, what instead maybe do we want to do here then? What's that? Okay, let u equal e to the x, and this is going to be what kind of integral? Well, it's got a square root. Okay, so it's definitely not arctangent. Is it arcsine or arcsecant, though? It is arcsine, right? There's nothing in front here, so it's got to be an arcsine. Okay, so let's see if we can rewrite this here. So I'm going to go ahead and pull this 2 coefficient out front and make it e to the x dx over, square root here. So our a value is 1, right, because it's just a 1, so the square root of 1 is 1, so 1 squared, minus, and then what's our u again? E to the x, right. E to the x quantity squared is e to the 2x. Okay, this is exponent rules, right? A power raised to another power, you multiply and simplify. So you can undo that multiplication by power to a power. You can go backwards, okay? And that's well. So, right, so we'll let u equal e to the x. So du is going to equal what? E to the x dx, okay? And so now, do we have e to the x dx in our problem? Yeah, we do. Okay, so 2 integral du over the square root of 1 squared minus u squared. Okay, and so this is in fact our arcsine. Remember, arcsine, does arcsine have the 1 over a in front of it? No, it does not. Okay, so it's just going to be 2 times arcsine of u over 1, u over a, plus c, and so that's twice the arcsine, substitute back in here, of e to the x plus c. Okay. So far, so good? Okay. Moving on then. let's take a look here at a definite integral. Okay, so now we got a definite integral from 0 to 1. All right, so this maybe looks like another arc sine, right? We've got the square root of 4 minus x squared there, so it's again a number minus a function. If we, excuse me, if we let u, okay, what would we want to let u be in this case? Just an x, right? Because again, it's x squared, so u would be just x. So du equals dx. Okay. But we have a problem. We don't have just dx here. We have x plus 4. So you're kind of right about arc sine here. What do we need to do with our numerator? Split it up. Split up our numerator. Exactly right. Okay. So this is equal to the integral from 0 to 1 of x over the square root of 4 minus x squared dx plus the integral from 0 to 1 of 4 over the square root of 4 minus x squared dx. Okay. What will this integral be? Okay, with u being what? Okay, so not x squared. This is going to be our arc sine. This here's our arc sine. We can pull that 4 out front, so it's 1 over square root of a squared minus, u squared here. Okay, so this is going to be our arc sine. What will this one be? This will be a u substitution with u equal to what? The 4 minus x squared. 4 minus x squared there, okay? Because the du then is going to leave us with an x dx, or something we can manipulate to be an x dx. This one right here, right? We can't just use u equal to 4 minus x squared because then our du would have an x dx in it, and again, it wouldn't work. Okay? So this is going to be great. So I'm going to do this one first. Okay, we'll take care of this one first. So I'm going to do it up here above it. Let u equal 4 minus x squared, so du equals negative 2x dx. We just have an x dx, so I'm going to say negative 1/2 du equals x dx there. Okay, I'm going to zoom in some more for y'all. Okay, that's a negative 1/2 du equals x dx. And so we end up with negative 1/2 integral, excuse me, of du over square root of u. Okay. I'm going to go ahead and also change my limits of integration here too. So plug the 0 in, it'll be 4. Plug the 1 in, it'll be 3. Okay. So plug the 0 in, it'll be 4. Plug the 1 in, it'll be 3. Okay, so far so good on that. Any questions on any of that? Just where we did from there to there, because again, this is pretty complex. All right. Now I'm going to, rather than go to this next one and start integrating this, I'm going to continue the thread like what we're working with here. Okay. Continue with this. So we've got negative 1/2 integral from 4 to 3. How should I rewrite this du over the square root of u so that we can really integrate it? U to the negative 1/2. Exactly right. Let's rewrite it like that. Much easier to integrate that way, right? So we have negative 1/2 times u to the positive 1/2 over 1/2. And we're going to evaluate that from 4 to 3. Okay, or if you like, you can flip the limits of integration around, make it from 3 to 4, and then this negative 1/2 will become a positive 1/2, right? Remember, you can flip your limits of integration. So in other words, I can make this 1/2 times u to the 1/2 over 1/2 from 3 to 4, right? Just flipping the limits of integration changes the sign from a negative 1/2 to a positive 1/2 there. So either way, you want to do that. Okay, so let's just, I guess, go ahead and finish this off. I'll cancel out the 1/2s there. And so we'll have 4 to the 1/2 minus 3 to the 1/2. Oops, I'm off the screen, sorry. Okay, so again, just trying to take care of this one thing, why not? Yes? So if you notice here, right, it was negative 1/2 times u to the 1/2 over 1/2 from 4 to 3. I then flipped my limits of integration from 3 to 4, so when I do that, it's just the opposite. It's the opposite. Okay? You don't need to do that, though. You can absolutely evaluate from here and, make it, negative 3 to the 1/2 minus negative 4 to the 1/2. You can evaluate from here if you want. I just chose to show you that just to remind you that you can flip your limits of integration, because every once in a while it can show up on a question on the AP and stuff like that, test too. I know these properties we want to make sure I'm refreshing your memories about and stuff. That's all. So you can flip your limits of integration and just get the opposite value for your integral. Okay, so that took care of this integral. Now let's continue down this track right here. In this case, so back up to where we were. Don't worry, we'll get back to the bottom there again. Okay. In this case, right, we said this was going to be an arc what? Sine. Okay, so I'm going to go ahead and pull that 4 out front, make it 1 over, and I'm going to go ahead and also rewrite the 4 as a 2 squared minus and then x quantity squared. Okay, dx like that. Okay. If you're going to use a substitution here, I would recommend that you use a different variable than u, because we've already technically used u in this part of our problem. And since we're talking in the same kind of same problem here, same universe, all right, we're going to use a different variable. The typical alternative variable you would use would be like v or like w or something like that. So I'm going to use v. So we're going to say let v equal x, and so d, whoops, and there I went, dv equals just 1 dx or dx there. Okay. And so this becomes then 4 integral, still from 0 to 1, of 1 over the square root of 2 squared minus v squared dv. Again, this might not be necessary, right? Some of you guys might be looking at this and say, Mr. Wade, why did you change the variables there? It wasn't necessary. You're right, it's not. Okay, you don't need to change the variables there if you don't want to, but it's just, it can be helpful. Okay, just the process we're doing here. Anywho, now we're ready to integrate this thing. Okay, so let's see. This is going to be an arc sine. Does arc sine have the 1 over a in front? No, it does not. Okay, so times arc sine of v over a, or u over a, all right? And then we're going to evaluate that from 0 to 1. Okay, so again, plus 4 arc sine 1 over 2 minus 4 arc sine 0 over 2. Okay. So you could be done at this point, right? I could just bring those down kind of to bring them together with the 4 to the 1/2 minus 3 to the 1/2. Whoops. Minus 4 arc sine of 0. Okay, so you can just bring that all down and circle that final answer. That's good. You don't need to continue from there. You may stop if it's a free response question. However, we can simplify further if it were a multiple choice. Right? So let me just pause right here before we do that. Any questions on the calculus part here? Yes, Gabe.
So,
The second integral?
yeah.
Second part. Okay.
If it was if v equals 2x, would we still have to change the limit of integration?
So for example, if this was 4x squared,
Yeah.
and so therefore v would be 2x, then you would need to divide. So if it was 2x here, you'd have 2 dx, so you'd have a 1/2 dv, and so this would not be a 4, it would be a 2. 4 times 1/2.
And then, so you wouldn't have to change the limit of integration?
Sorry, yes. If you use that method where you change limits, yes, you would need to change the limits, because if it's 2x, then the limits of integration would change. Yep. Okay? Good question. Absolutely. Okay, so another question in the calculus. All right, so now, square root of 4, 2, square root of 3, square root of 3, right? Okay? Arc sine of 1/2. Ooh, right? We haven't done this in a while. All right. Well, what special right triangle has the ratio of 1/2 in it? 30, 60, 90. Okay. So we'll say that's 30, that's 60. There's 1, there's 2, there's the square root of 3. Okay. So arc sine of 1/2 is going to equal some angle theta. So in other words, 1/2 is sine of what angle theta? The 30 degrees. But of course, we're in calculus, so we do all of our calculations in radians. 4 times pi over 6. Yep. Minus 4 times, all right, arc sine of 0. So now let's ask the same question. We don't really have a reference triangle for this, but sine of what angle gives us 0? 0. So times 0. Okay. And so we get 2 minus the square root of 3 plus 2 pi over 3. Answers with both square roots and pi. That's great. That's really great. All right, moving on. Here we go. Here we go. All right. Number 4. All right. Could I let u equal x squared minus 4x plus 7? Could, but then I'm going to end up with 2x minus 4 for my du. I don't have a 2x minus 4 in my numerator here. Okay, so let u equal x squared minus 4x plus 7. Du equals 2x minus 4 dx. So nope, that's not going to work. We don't have a 2x minus 4 dx, just a dx. Okay, you ready for this one? Close. We're going to complete the square. Collective groans from the audience. There we go. I know. Yes. Yes, your anger is strong.
Do you really not remember this?
All right, so
This is the worst thing ever.
So x squared minus 4x plus 7 is not a perfect square, right? Do you remember how we obtain? What do we do with our b? It's half the b value squared, and so we want this to be x squared minus 4x plus 4, right? That is a perfect square from this, okay? But then I just brought in this plus 4 from nowhere, so I'm going to also subtract 4 to kind of balance that out, and then plus 7, right? So all I've done here is I've taken the x squared minus 4x plus 7, I rewrote it equivalently, right? I'm adding 0 in here, but I'm adding 0 in a tricky way so that I create this thing to be a perfect square. Okay? Half b squared, okay, is that. Remember that term that you want to do to complete that square. It's 1/2 the b term squared. Okay? And so there it is. So what does this factor to be? Better be a perfect square. And then the minus 4 and the plus 7, we're going to keep them together. That'll be plus 3. So x minus 2 quantity squared plus 3 creates that perfect square that we all love. Okay. Now that we complete the square, what does this integral seem to be a candidate for, I guess? Arctangent. Yes, this is arctangent. Okay? So, arctangent, what is our a? Root 3. Very good. Okay? We have 3. That is a perfect square of the square root of 3. So, okay. And then our u will be what? X minus 2. Du will just be dx. Thank goodness we have that at least to help us. So we'll have du over u squared plus the square root of 3 quantity squared there. Okay. So let's see. When I integrate and get arctangent, does arctangent have a 1 over a in front of it? Yes. 1 over the square root of 3 arctan u over the square root of 3 plus c, or 1 over the square root of 3 arctangent of the quantity x minus 2 over the square root of 3 plus c. Whew. Calculus really does bring in like pretty much everything that you've ever learned, at least in high school math, unless you took statistics. We don't really do any statistics stuff, right? But I mean, there's kind of some statistics. I mean, talk about area under the curve and your, bell curve there, and those, accumulated, areas and stuff like that. I mean, there's some calculus involved there too. Okay, so it even creeps its way into statistics. All right. Questions on any of that? All right, next problem here. All right,
Fun stuff.
example 5. Find the displacement, in other words, the net displacement, right, of a particle whose velocity is modeled by v of t equal to that. Okay? How do we find net displacement of a particle given the velocity? We don't. We give up. Drop the class.
Sounds about right.
What do we do? Integrate the velocity, the rate. Exactly right. Okay, we're just going to integrate the velocity here. Integrate from 0 to 2 of v of t dt. Okay, which I guess I shouldn't have done like that because we need to be able to manipulate things here. Oh gosh. Okay. Remember that net displacement is the integral from a to b of v of t dt. Okay. Net displacement is that time when if I step left and I step right back to my original position, what is my net displacement? 0. Okay. Total distance traveled would be 2. That's the integral of the absolute value of the velocity, or we also know the absolute value of velocity as the speed. Okay, ka-chow. All right, so, ka-chow. More like Owen Wilson would say it. All right, anyway. So, how do we proceed from here?
Just get points wrong.
Well,
Just
take the L, Mario.
throw your pencil. Just throw your pencil off. There's no point.
The degree of the top and the degree of the bottom are the same. Oh, Mr. Webb, we talked about log division yesterday. I don't want to do it today. Yes.
Sarah, I'm glad you agree with this.
Mario, I think your idea is better.
Just play the game and try to get the pencil stuck in the groove. You'll get better odds.
Wait, Mr. Wood, will you give us points for doing this question right on the test if we get a pencil stuck in the ceiling?
You do it.
It's like, answer this question correctly or get a pencil stuck in the ceiling. Oh my. All right, so anyway, we integrate from 0 to 3. All right, so I did the long division here, right? Hopefully correctly. Okay, yeah, looks good, I think. So, all right, so it's 3 plus 4t over t squared plus, did I miss something?
Yeah, it's the integral from 0 to 2.
Thank you. There it is. See?
See?
I started thinking of it.
Throw
Throw the pens. I'm going to throw a pen. All right, so anyway. dt, of course. Don't forget the dt's.
Oh my god.
Okay, now, to integrate this thing, I'm not going to do it because we're running out of time and I want to make sure I get to the back page here. Integral of 3, easy enough, right? It's 3t. What would be the thing we want to do here? So we're going to break up this integral, make it 0 to 2 of 3 dt, plus the integral from 0 to 2, and then of 4t over t squared plus 4 dt. What are we going to use here to integrate this? Is it arctangent? No, it wasn't. That was right, Sean. Okay, it is not an arctangent here. Okay? It's Sean? Him? No, it's, yeah, the integral, so t squared plus 4, the denominator certainly looks like arctangent, but what's the numerator for arctangent got to be?
A squared.
The numerator. 1 or like a du, right? Just 1 du. We have a t up here, right? If I make that, our u here would be t, du would be dt, all right, which we would just have that, but then we have nothing to do with this. So it is, in fact, going to be a let u equal t squared plus 4, so du equals 2t dt, or in other words, 1/2 du equals t dt. And so we end up with, I'm going to have to go down here because I wrote right in my way there, 3t evaluate from 0 to 2, plus the integral. I'm going to pull the 4 out front. Oh, there's a 1/2 as well. Oh, I didn't leave myself in a space. Mr. Wade. 3t evaluate from 0 to 2 plus 4 times 1/2 the integral of 1 over u du. Okay, and I will leave the rest for you to ponder. I'll put, I guess, the new limits of integration. 0 plus 4 is 4. 2 squared is 8. No, I'm going to save time by not continuing any further. If your test is during a 2-hour early dismissal day and you're crunched for time, maybe. Maybe. But we have to I have 10 minutes to do this back page here. Actually, the back page, we're not going to do all those integrals. We're just going to, like, discuss them, okay? So, but there's that one. All right, you guys get the idea. It's going to be natural log of absolute value of u from 4 to 8.
This looks like everything we've learned.
Yes. All right. And now to the back.
You now have 20 rulers. Or we're looking at the back of this at the very beginning. Where, like,
Guidelines for integration. Number 1, memorize your integration formulas. You now have 20, okay? Including those inverse trig ones, you now have 20 rules. Number 2, find an integration formula that resembles all or part of the integrand, and by, and this is the hard part, trial and error. Find a choice of u that will make the integrand conform to the formula, right? So we have a limited number of things we can integrate. 20 things that we can integrate, okay? Only 20. So your goal then is, if you look at a problem and it does not look like one of those 20 things, either can you manipulate it to be one of those 20 things? Well, actually, it's got to be, can you manipulate it to be one of those 20 things? That's how you need to do that, okay? Sometimes it requires breaking up a numerator. Sometimes it requires long division. Sometimes it requires a u substitution. Sometimes it requires a combination of all those, okay? Things. So it's quite tricky. And of course, in this particular problem, there are 2 that we cannot do, okay? And we do not know how to do, okay? And then finally, step 3, if you cannot find a u substitution that works, try altering the integrand, right? So you might try a trigonometric identity, multiplying and dividing by the same quantity, or adding and subtracting by the same quantity. Be creative, but patient most of all. It's the second time we've seen that, okay? So, example 6, describe how to evaluate the following integrals using the formulas and techniques we have studied so far. Hint, 2 of the following cannot be integrated as of yet. So again, I would give you more time to do this, look at it on your own and ponder it, but we just don't have the luxury to do that. So we're going to go through this here ourselves. So letter A, what does it look like this is going to be? Arcsecant, okay? Arcsecant. We've got u squared minus a. That u is right in front of the square root there, so absolutely this is going to be arcsecant. I'm not going to actually do it. Well, I guess that is it in this case. It'll be absolute value plus c. But anyway, we're not going to actually do these. We're just going to discuss how to do them. But, well, there it is, okay? All right.
You can't do it.
What about letter B?
No.
U substitution with u equal to what? X squared minus 1.
No, you just give up.
Okay, and again, I'm going to put this in parentheses or quotations because this is not exactly what it's going to be, but it would be, it's going to end up being, yes, a square root of u in the denominator. So du over the square root of u, or in other words, the integral of u to the 1/2 du. Negative 1/2, sorry, thank you, negative 1/2. Okay? All right, letter C. What would be our strategy here? Well, arcsine would be if we had not x squared minus 1. That would be if we had, so arcsine would be dx over square root of 1 minus x squared. And yes, we could factor a negative out here. This would be equal to dx over the square root of negative 1 times 1 minus x squared. But then we have that negative 1 kind of lingering in front there. We can't really do anything with that. Okay, if we try and break that square root of negative 1 out, we're taking the square root of a negative 1, which would be imaginary. So how do we, so this one we could integrate. That would be arcsine, or arcsecant, or arcsine of x, sorry. Okay, plus c. But how do we integrate this one, though? Yeah, impossible. We don't know how to do it yet, at least. Okay, that one's not. So there's the one that doesn't work. All right. Letter D. How will we integrate this one? U substitution, let u equal what? E to the x plus 1. And so we're going to end up with du over u. So this is a natural log. It's going to end up being a natural log. Okay. What about letter E? What's that one? It is arctangent. Yes, it is arctangent. So again, if I rewrite this a little bit carefully here, we have e to the x over, this is e to the x squared plus 1. So there's our function squared plus 1 dx. So we're going to let u equal e to the x, or du is e to the x dx. This is, in fact, an arctangent of x. Okay, for that one. All right. How about letter F? Can we integrate this one? Oh, just because Mr. Whitmire asks, can we integrate it, doesn't mean that's the one. We can integrate this one.
Yeah, long division, right?
Yeah, I wouldn't do long division here, but it's the right idea. We want to break up our numerator. We want to break up our numerator here. Make it e to the x over e to the x plus 1 over e to the x dx. So we end up with the integral of 1 plus e to the negative x dx. And you can integrate both of those. Integral of 1 is x. Integral of e to the negative x, that would require a small u substitution. ... You get the idea. All right, letter G. How we integrate this one? Can we integrate this one? No. It is a u substitution here. We should let u equal what? Natural log of x, because its derivative is what? 1 over x dx, or dx over x, which is what we have right there. Okay, so this is going to end up being just the integral of 1 over u du. Okay? All right, how about the integral of the natural log of x? This one is a no. We do not know how to integrate the natural log of x. We can take its derivative. We can integrate 1 over x, and that is the natural log of x. But if we ask to integrate the natural log of x, we don't have a function for that. Okay, so, and then therefore, right, the next one must be possible. What will our u be here? Natural log of x, so du equals 1 over x dx, which we have right there. Okay, and so this would just be the integral of u, du. That's nice. Okay, we made it. Did everyone understand everything? No. I'll take that as a yes. All right, so your homework will be posted to Google Classroom. And of course, I would recommend you start looking at the review.